my talk today is on minimum description length analysis. And that's such a long phrase with so many syllables and consonants that nobody says minimum description length more than 2 or 3 times. We always say MDL, and so I will say MDL. So I want to talk about MDL, which is not about a particular language, and it's not even really part of linguistics, but it's an idea that I encountered about 25 years ago, a little bit more. And it really changed the way I think about linguistics in some important respects. So I want to share that with you. I found some of it rather difficult to understand at first, so I think I can share some of the steps it took me as a linguist to understand what it's about. That's my goal for today. So there'll be 3 parts to my presentation. The first is the big idea, which is MDL. And MDL, one way to look at it is that it gives us a way to calculate the 2 things that we probably care most about when we're evaluating a grammar, the simplicity of the grammar and how well the grammar fits the data. That's an interesting verb, to fit, in this case, to fit the data. I'd be curious what the metaphor is in Russian for it, because it's a peculiar metaphor. But in any event, I think we understand what it means for a theory or a model, or as we linguists say, a grammar. How well does it fit the data? So these are 2 things we look for in a theory, and MDL gives us new insight into those ideas. There's another reason that I'm interested in MDL, and that is that it encourages us to think about how we can identify what needs to be learned from some data. I think you'll see what I mean by that. That's a very abstract statement, but I think it'll become more concrete as we go along. And that means it provides some useful ideas about how to automate the process of going from data to grammar. And that's a question that I think is very interesting. I think it's important for linguistics. So the first topic, after I present the general idea, I'm going to talk about 2 topics. The first is word discovery. And what I mean by that, the phrase word discovery is often used. Sometimes the phrase word breaking is used. And what I mean by that is, suppose we have as an input a long text which doesn't have any spaces between the words. I'm going to be looking at cases where we have lists of sentences, which are a couple hundred letters long, and we've got tens of thousands of these. So it's broken up into sentences, but with no indication of where the words are broken. So in certain respects, it's a lot like what the child hears. There are no spaces between words. So we'll look at things like what you see in 3 here. The Fulton County grand jury said Friday, and so forth and so on. I can read that because I know the language, and you do too. But in general, how do we figure out what the words are when all we have is text? That's part of what a linguistic analysis ought to be, it seems to me. So to do that, I'll look at a very simple model for language and see what it gets right, what it gets wrong. And what it gets wrong tells us a lot. I'm really interested in when models fail, and I will try to communicate that feeling with you. And the work that got me excited about this and got me launched was work by 2 different people. They were classmates at the same time, but they were working independently in computer science at MIT in the mid-1990s. One was Michael Brent, the other was Carl DeMarkin. If you're interested, you could pursue this. Carl Markin's dissertation is online. It's really, really interesting. The second example I'm going to talk with you about is morphology discovery, which is the work that I've been working on and off for 25 years. And I was motivated and inspired by the work of Brent and DeMarkin. So there, the input is a list of words from a language, and the goal is to find the stems and the prefixes and the suffix and principles of how they get put together. So that's what I want to talk to you about today. And the first part then is MDL, the big idea, or the idea in any event. The idea comes from a field that's called machine learning, which is a field that became conscious of itself in the mid-1980s. It's a field that has 1 foot in statistics and 1 foot in computer science. Statistics in the United States is typically in a separate academic department from mathematics, because many of the problems are more applied than problems that are loved by mathematicians. In any event, machine learning is a synthesis of statistics and computer science. And back in the late 1970s, Jorma Rissanen, who was a Finnish-American statistician who worked for IBM Research for his whole career, he developed this model and continued to work on it till his death. In making these slides just this week, I discovered that he passed away in 2020. I'm very sad to hear it. He was a very nice person. So as I said before, good empirical ideas ought to have two properties that we look for. They should be simple and they should fit the data well. And MDL kind of begins with that assumption, or with that set of prejudices. And if we apply this to linguistics, we can use the word grammar. I'll use the word grammar basically to mean our analysis that we're interested in developing. And then we've got a set of data, and linguists often call the data a corpus. So I'll usually say corpus. I might say data as well, but I mean the two words mean the same thing. So we want a grammar that's simple and a grammar that fits the data well. So here's the thing. MDL does not, well, say it positively first. MDL can evaluate a pair of two things, the grammar and the data, the grammar and the corpus. It can evaluate how good this pair is working together, but it doesn't give us a grammar. It's not a discovery procedure in any sense, but it can be very helpful inside a discovery procedure. And so I'll try to show you how MDL encourages us to explore empirical hypotheses about learning language structure from natural data. When I say natural data, I mean data that the linguist didn't create by themselves. They may have gone out and created a corpus from the internet or from interviewing people or what have you, but it's not toy data. It's not data created by the linguist, but rather is data that exists independently. It's data in the real world, so to speak. And so MDL encourages us to find ways to figure out how you could develop methods from going from data to grammar. So if we want to put together these two ideas, the grammar should be simple, they should fit the data well. We need to, if we're going to do MDL, we need to combine these two questions. We need to come up with a way to quantify them. That sounds crazy, but that's what we're going to do. We need to quantify them, and we're going to add them together. To add them together requires that they be measured with the same units. We can't measure one with kilograms, the other with kilometers. So we need a common unit, and luckily enough, there is a common unit, and it's what's called the bit in information theory. So we're going to come up with methods to evaluate or measure the simplicity and how well a grammar fits the data. We will add the two together, and then we will try to minimize the sum. But that's not a familiar notion for most linguists. So what I mean by that is we'll consider different grammars, and different grammars will lead to different sums of these two numbers, the sum of number one and number two. Put them together. What we'd like to find is the grammar for which this sum is as small as possible. That's the big idea behind MDL. So again, we need to find a way to quantify these 2 points, 1 and 2. Linguists are generally not very comfortable with that step, quantify these very abstract notions, and that's what we'll try to do. We'll try to measure the grammar's simplicity, and we'll try to measure how well a grammar fits the data. And to do that, we need probability. So that's what I'm going to spend the next 5 or 10 minutes talking about. And if you're uncomfortable with the math, you shouldn't be. And I'm going to focus this or aim this towards people who don't have much familiarity with it, but you should stick with me. And for those of you who are familiar with mathematics, I'll have a couple of slides that are meant for you, not for the others. Okay, so Probability, slide number 1. The most important idea, the most important technical term here is a distribution. And a distribution is a set of numbers which are greater than or equal to 0. So they're not negative, and they sum to 1. So just a definition. So here's some examples. 1/2 and 1/2, that's a distribution. They're positive and they sum to 1. Second example is 1/4, 1/4, 1/6, 1/6, 1/6. Well, the first two numbers sum to 1/2, and the 3 1/6 sum to 1/2, so they sum to 1. That's great. Take the third example, a little bit more of a stretch. Consider how we can add together 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. As you keep adding these and you get to the end of infinity, this sum is, in the limit, as a mathematician would say, is 1. So it's perfectly fine to have infinite distributions. And since we're linguists and we care about things that are infinite, like the set of sentences in a language, infinite sets are really important. And even when the sets aren't infinite, they're big because language has lots of options in it. So if we're looking at the set of all the words in a language, it may be infinite. It's certainly going to be large. And if every item has a probability and they sum to 1, you can see those probabilities are going to be small. I'll come back to that. But so that's a distribution. And now a second definition, a probabilistic grammar. This is maybe the most important idea that I'm going to talk about if you've never encountered it before. MDL presumes it or is based on it, that it's not a very familiar notion to most linguists. A probabilistic grammar is one that assigns a probability to every item that it generates. And these probabilities form a distribution. So imagine that. Imagine your favorite grammar. And when you build it, you also have to assign, or the grammar itself has to assign a number to everything it generates, and those numbers have to add to 1, and you're responsible for making sure they add to 1. That's a probabilistic grammar. Okay, now here's a second point, which is important, but not very technical, and that's this. Probability, as we're going to talk about it today, has nothing to do with chance or randomness, or if you're a sociolinguist, variation. There's nothing to do with that, and yet that's how it was taught to us in high school. But that's the wrong road to go down. We're not talking about chance or randomness. It has everything to do with what a model or a grammar says should appear in reality or might appear in reality. The idea is this: the best grammar for a set of data is the one that assigns the highest probability to that data, all other things being equal. Because models, or grammars, look out and they imagine all sorts of possibilities. And the one that expects what reality is the one that we care for the most. Grammars will generate a lot of things, some of them with low probability, some with high probability. And that's the grammar's way of saying what its expectations are of reality. So the one that expects reality, closest to what reality is the one that we want to embrace. The point to this is that last sentence there, this crucial idea. The best grammar for a set of data is the one that assigns the highest probability to the data. And that means that we use probability to test grammars, not to evaluate the data. And I don't think there's any linguist who doesn't do computational linguistics who understands that. It's so easy to think that a probabilistic grammar is out there to assign probabilities to sentences. Yeah, it does that, but that's not what we're using it for. We're using probability to evaluate grammars. So bear that in mind. Probability 3, okay, so there's that crucial idea. You've already heard it. The best grammar is the one that assigns the highest probability to the data we have, all other things being equal. And here is a footnote, but again, an important one. I'm not going to go down this alley, but you might. This is an alternative to thinking that grammars should distinguish between grammatical and ungrammatical sentences. You know, most of us grew up being told that that's the point of a grammar in a generative grammar, to separate the two. So the grammar should only generate grammatical. And this approach says, no, that's not what it's about. The grammars should assign probabilities to lots of things, and it doesn't distinguish grammatical from ungrammatical. It's tested, however, on the grounds of how well it assigns probability to sentences that exist. So that has important epistemological consequences, none of which really I will talk about today, but that's just a pointer to you. Okay, a little more probability, a little more math, but it's still high school level math, and that's logarithms. Many people, when they graduate from high school, they are very happy that they will never have to hear that word again. But if that was you, it's come back. And computer scientists only care about base 2 logarithms. If you remember what that means, that's great. If you don't, it doesn't matter. So the probabilities that we assign to sentences and words and all the things that we care about in linguistics are very, very small. I've already told you why, because there are so many of them, and they have to sum to 1.0. So numbers between 0 and 1 are all negative. So we take the logarithms between 0 and 1, of all our probabilities, which lie between 0 and 1, we take their logarithms, and they're all negative numbers. So we multiply by -1 because nobody likes negative numbers. So we get this positive log, and I'm going to call that a plog. I made that up, and if you will use it yourself, I would be very grateful. So let's look here at the table on the right. So a probability of 0.5 is a half. 1/2 is equal to 2 to the -1. The log of that is -1, but fortunately the plog is 1. If we go to the second line, 0.25 is also known as 1/4, and that's 2 to the -2. And the log of that is -2, and the plog is 2. The third number is 1/8, which is 2 to the -3. Its log is -3, a plog of 3. You see the picture. As the fraction gets smaller and smaller, its plog gets bigger. A million. The plog of 1/1,000,000 is very close to 20. So since we care about high probabilities, we will be looking for small plogs. Okay, so bear that in mind. And here's another picture to show the same thing. On the left side, there's a graph, and this is a plog, -1 times the log, and our probabilities always lie between 0 and 1. So the plogs are small when the probability is close to 1, which is very, very high. And then the plogs get big, 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 big when the probabilities are small. Okay. All right, now we get to the question, what does it mean to say or to ask how well the grammar fits the data? So we want that probability to be high. So that means the plog should be small. The smaller the plog that the grammar assigns to the data, the better the grammar fits the data. Okay. And it turns out that that number, a plog, has a natural unit. I mentioned this before. It's a bit. If you read any introduction to information theory, you'll learn more about it. For our purposes, just take my word for it. So probabilistic grammars assign a number of bits to the data that they explore, the data that you give to them and ask them to parse, so to speak. Another way to say it is this, and this is kind of deep and I won't really go into it, but I hope you get the intuition behind it. This quantity, the plog of the probability of the data, is, from the point of view of information theory, it is the amount of information in that data that's not explained by the grammar. And that's why we want to minimize it, because we want to we want our grammar to extract everything that it possibly can from the message, but it can't be 0 because, of course, it is a message. So there's a real message. If you say, help me, you know, that's a message. There's a meaning. The grammar can't extract that. So this kind of information theory is trying, what we will be doing is to try to extract linguistic structure, leaving behind every other structure, which is the message, essentially. Okay, we're halfway done, or a little more. We have to ask, how do we measure the complexity of the grammar, and how do we measure it in bits? So this is going to sound like magic, and if you don't get it quite, it doesn't matter. It really doesn't matter, but I'm going to just run through it anyway. So you have a grammar, you've got some way that you like to write grammars, and you have different symbols in it. You count the number of symbols and call that S. And then you've got a grammar, and you look at your grammar, it goes on for pages maybe, and you count the number of symbols in your grammar, and you multiply that second number, call it N. You multiply N by the log of S, and then to get the probability of that grammar, hold on for a second, it's just 1 over 2 to the N times log S. Okay. But if we do this plug stuff again, that gets rid of that crazy fraction, and we're back to N log S. And log S is the number of symbols. And nobody's ever asked you to think about how many different symbols you have in your grammar, but it actually is important. If you only use 0 and 1, which is what computers do, as you know, then S is 2, and log of 2 is just equal to 1. So the complexity of a grammar just turns out to be the number of symbols if you express it in a computer language, which is just wild. Just accept it for our purposes. Okay, now we're really almost done. We're at the end of the math. And so here's what we're doing. Given some data, D, and a probabilistic grammar, G, that works for your data, other data, you calculate the plog, -1 times the log probability of the data, as far as your grammar G is concerned, plus the length of the grammar. That's what's called the description length of the data with that grammar. And then the goal is to choose the grammar that minimizes the sum. And that's it. That's it. I've been living with it long enough that seems simple now. It may seem not so simple to you, but that's it. And if we were truly mathy people, mathematicians would much prefer that I write it this way. So this is what a mathematician would write for everything I've just said. They would say G hat is the grammar we're looking for, and it's equal to the argmin, meaning the grammar that minimizes this quantity, the base 2 log of the probability of the data plus the length of the grammar. But that's just to tout how nice mathematics might be. And then one extra slide, and this is only if you've ever encountered Bayes' rule in a class and wondered who cares about Bayes' rule. Well, it turns out that Bayes' rule kind of is MDL, or maybe a better way. MDL is Bayes' rule. Bayes' rule gives you MDL. And if you haven't run into Bayes' rule, just forget it. But Bayes' rule says this: the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. It's really just an algebraic manipulation. There's nothing deep about it. But if we plug in grammar for A and data for B, then it starts sounding like linguistics, because it says the probability of a grammar given the data is equal to the probability of the data given the grammar. And that we know how to do because our grammar is probabilistic, times the probability of the grammar. And I already told you how to calculate the probability of the grammar, divided by the probability of the data. Okay, so the best grammar is the one that maximizes the numerator, the guy on top. We don't need to worry about the probability of the data because it's going to be fixed. We just choose a set of data and it's fixed. But we're going to vary our grammars. So we want the one that maximizes the numerator. And if we multiply by -1 and take a log, then we just get this equation at the bottom. And if you read it there, it says the plog of the data plus the length of the grammar. We want to minimize that. That's just MDL. So a few steps here. It's very cool, but if you haven't run into this, then you probably don't need to worry about it today. So let's turn now to the two to two particular examples that have meant a lot to me personally. The first is how I encountered this idea in the first place in the work of Karl Demarkin. And so this is the problem of word discovery. And so I want to start with a little bit of an exercise with you. I want you to be a little bit familiar with, so that you can understand what I mean when I say, well, let's measure the length of a list of words. Okay, so here's the first thing. It's a little bit magical. A letter, how much does it cost to, and bits, how much does a single letter cost? The answer is about 6. And you might say, well, 6, it sounds like Bitcoin or something. 6 what? 6 bits. Well, why 6? Well, it's 6 because, well, in English, we've got 26 letters in the alphabet. We've got uppercase and lowercase. We've got digits from 0 to 9. We've got some punctuation. And it's about 68. And 64 just happens to be 2 to the 6th. And since we're doing everything with log 2, that's why you get 6. So each letter costs 6, like 6.1 or 6.05 bits. And then how long is a word? Well, fortunately, we know how to measure that. It's just the number of letters, but actually not. You have to add 1 extra letter at the end to mark that the word is over. So, you know, the word dog has a mark at the end, which indicates that it's over and it's not part of doghouse or doggerel or anything else. So if you've got a word of length L, the number of bits it takes is L plus 1, not 7, 6. I don't know how that 7 got in there. It's 6. L plus 1 times 6. And the plus 1 marks that, is that thing that marks that the word is done. And the cost in bits, or the quantity in bits of a list, is the sum. You just sum these bit counts for all the words. So here's a little example of a list with 3 words: dog, cat, and horse. Dog is 24 bits, cat is 24, horse is 36, and the total is 84. So that's not hard. But I want you to be able to say, yeah, I know how to count the number of bits in a list of words. Okay, so word discovery. We have a text. We want to discover the words or the morphemes. The chunks is the word I tend to use. And so if we look at the particular corpus I have in mind, it has 50,000 sentences, and each is a couple hundred letters long, like that sentence there in 3. The Fulton County grand jury said Friday, blah, blah, blah. Now, since you are linguists, you know that it is not obvious what a word is in a language you've never looked at, and how a word differs from a morpheme. And you might not even believe in morphemes. You might not even believe in words. And that's okay. I know that too. But we're going to explore what a simple system does, and we're going to try to figure out what we can learn from it. So the way we do this is we're going to begin with a lexicon, and it's just the letters, those 66 or whatever, 67 letters, A to Z and A to Z. We'll just start with a minimal lexicon, and then we're going to work bottom up. I say we, but it's really the program. The algorithm is going to come up with longer and longer hypotheses for what the words are in this language that lies behind the corpus. And we're giving our algorithm only one way to account for the generalizations it observes in the data. We tell it, you can hypothesize words. Those are strings of letters. And we don't tell it anything about morphology. It knows nothing about word internal structure. Words have no internal structure for it. And it knows nothing about syntax. It doesn't know that some words like to be next to one another or whatever. It knows nothing. We only give it one piece of intelligence, and that's it. So we want to see what it does with that very small piece of intelligence. So each word is assigned a probability by the algorithm, not by us. And it's based on how often it finds that particular string in the corpus that it has parsed, as we'll say. And the probability of an utterance is the product. We multiply them. It's the product of the probabilities of all the words in that sentence. And we do that, of course, for each sentence. So, for example, suppose the string is the train. That's not a very long sentence, but that's okay. So on iteration 1, the only words that it has in its lexicon are individual letters. And so it sees 8 words, THETRAIN. So that's the probability of 8 very small numbers. On the second iteration, as you'll see, it will have already hypothesized the words TH and the words IN, and it will now parse that word in a different way. It'll say, aha, it has 6 words in it. TH is a word, and E is a word, and T is a word, and R is a word, and AI is a word, and N is a word. So it will multiply 6 numbers together. Well, when you multiply 6 numbers together, it's a bigger number than if you multiply 8. On a later iteration, it will already have hypothesized THE and TR. And now the best parse is THE, which is in fact correct, and TR and AI and N. Okay, so I'm just telling you what the algorithm is going to be doing. So that's what it's going to be doing, making bigger and bigger chunks, and doing that in order for the probability to get bigger. And the length of the grammar then is just the length of all those words that it hypothesizes. And it contains the word's frequency because it uses that to calculate a probability. So the description length of the data given the grammar is the sum of the lengths of all the words it hypothesizes, and then the plog that it assigns to that corpus with its current lexicon. Okay. You're going to see this in just a moment in very concrete terms, but I'm trying to explain to you what it is that you're going to be looking at. So we cycle through the data, and each time we add candidates to the lexicon, and each iteration, I'll show you some of the words it adds, but we keep all the words that were there before. It may not always use them all, but it doesn't forget what it had on earlier iterations. And I will show you that. And on each iteration, the algorithm computes the description length. And as long as that's getting smaller, it continues. But when it doesn't get smaller, it stops. Okay, let's see. I'm going to skip that. I've already explained that to you. Okay, so on the first iteration, here's what it finds. These are the most frequent words that it finds together. TH is the most frequent. Not a surprise. HE is the next most frequent. IN, which happens to be a word, is next. And ER, which happens to be a morpheme. And AN, which happens to be a word. Okay, but most of these are they're just frequent pairs of letters. And yesterday I ran a dump of Wikipedia, which is about the same length as the corpus from English. And so you see here, no, and it's the same kind of frequent pairs of letters in Russian or in English or really any other letter. In English, we have the most frequent word as the, and not surprisingly, it pops up as the first new word, the first, well, it's not the first, this is our second iteration and it's at the top of that list. So THE is a word and AND is a word, and I see ING, which is a morpheme. So, okay, it's doing reasonable stuff. It's not yet words, only a small number of morphemes. Russian, see about the same thing. You see 19 and 18 and 20, which is a strong hint that that we have a lot of dates in this Wikipedia text. But nothing other than that, no great surprises. The next iteration just keeps on doing the same thing. There's one point here that's interesting. THE, capital THE, is now identified in iteration 3. It has no idea that lowercase t and uppercase t are closely related. It just treats it as a separate word. And we've got a suffix ation here as well. In Russian, well, you see what we've got. No great shakes here, but it's roughly comparable. Okay, skip ahead to iteration 10. Here we see something interesting in English. We have the EDTHE. So why do we have EDTHE here? And the answer is because it knows nothing except chunks. It doesn't know morphology. It doesn't know syntax. And when you have a sentence like dropped the ball, the EDTHE has a much higher frequency than dropped ever does. So because of the limitations of its sophistication, it thinks EDTHE is a chunk, and it will take it a lot more thought before it stops doing that. Okay, Russian. Oh yeah, here you see Wikipedia. You can see it's showing its colors here. 366, there are probably 366 articles in the text. Okay, and jump down to iteration 100. Now these are looking a little bit better. The words are rest, gree is not a word, southern is a word, whose, length, out, it's not out there, that's out plus a period. So it's putting, it already knew out, I'm sure, but now it's come out with out plus a period. Command, Tim, address with only one S, S from the, that's another example, just like the EDTHE on an earlier pass. And in Russian, similar stuff here. Pavlov here. Okay. Jump up to iteration 400. Yeah, we've got lots of nice words here, but we've got too many sequences of words. And as I'm going to tell you in about a minute, the lexicon is getting clogged up with these sequences of words. The lexicon shouldn't have to be responsible for it, but we didn't give our algorithm enough intelligence. And so it's doing the best it can under the conditions that we set for it. So this is its final iteration, or rather, these are the words it comes up with on its final iteration. Wartime, smaller than, fusion power, tonight, period. So yeah, it's just more of the same thing. Here's this final set of candidates on that corpus that's about the same size here. Material. Yeah. So here is one of the first sentences from the English corpus. And the original is at the bottom of the slide. You know, it says, this is one of the major items in the Fulton County General Assistance Program. And at the top of the slide, I've given what this word breaking program thought. And the red letters show when it's made its words too big. This is, should be 2 words. One of the, should be 3 words. But, you know, is it good, is it bad? You know, there is this thing, you fall in love with your algorithm. This is a problem that computational linguists have, and I know I have it myself. You love your algorithm so much, you begin to think, Fulton County, it thought that was a word, but it's 2 words. Oh, well, maybe it really is 1 word. Maybe it's right and we're wrong. Well, you know, you can't act that way, but it's very tempting to. And in blue, you see some other mistakes. Distribute these funds is what it ought to be. But the E didn't get connected to distribute. It got attached to THE, which happened to be a word, but it's not the word here. So it's just wrong. We can sort of know why, but it almost doesn't matter. And here we've got another error of this, exactly the sort. We know why it made that error, S followed by OF. All right, and yeah, so here's the first 6 sentences of the Wikipedia in Russian, if you want to take a look at it. I think the lesson here is kind of comparable to what we see in English. Excuse me. Okay. It is important when you do computational linguistics to evaluate, to quantify how well the program is doing. And there are different ways of quantifying it. But I want to focus on the last one here, which is 0.1298. That's the English, not the Russian. It's probably comparable. That is telling us that it has discovered approximately 13% of the words. And honestly, that's terrible, right? 13% of the words is found. But there's a perfectly good reason, and which sort of excuses things, but not completely. That is, MDL stops it from learning anything that occurs less than 5 times because it got clogged up with these syntactic strings. And most words in a corpus only occur once or twice. And if you take all the words that occur only once, twice, 3 or 4 times, you're up to like 80% of the words of the corpus. So this is wonderful as far as it goes, but it doesn't go far enough. Let me show you one more thing here. I just made this slide just before we got online. I want you to see how its thought process evolves as it goes through. So this is what are you seeing here? You're seeing words that it comes up with. And I was interested in how it dealt with psycho and psychology and psychoanalytic and stuff, not for any particular reason. And each word here, what you see is what it is doing on a particular iteration. So take the word psycho. It comes in on the 35th iteration, and it comes from psi. So if you look up at psi, you can see it started out at 138. But on iteration 35, it dropped down to 47. It lost a large number there. And some of them went to psycho. And then it lost quite a few 20 iterations later because it learned psychological. So a lot of things that were psycho are no longer psycho, now they're psychological. And then later, psycho loses out to psycholog, and then it loses out to psychology and psychoanalytic and so forth. The numbers go up and down. On each iteration, it does the best it can. Okay, so I hope that's clear what it's doing. And okay, so that's the end of the second part. Now I want to turn to the third part, which is morphology discovery. And so this is more my work, inspired by this earlier work, because I said to myself, as you can see, the system isn't going to get better until it learns about syntax and morphology. And about 25 years ago, I said to myself, well, morphology, that might take 5 years, but it's taken a lot longer than that. I'm going to skip this slide. You may know this from Chomsky's syntactic structures. All I want to say, if you know this, is I believe in this third picture here, that linguistic theory should be able to say which grammar is better than, given 2 grammars, which one is better given the data. And MDL, I think, is the right way to ask that question. So we're going to learn morphology, and we're going to develop an algorithm that finds ways of successively or iteratively decreasing the description length. And I'm going to use the concept of a signature. And by signature, I mean the following. There you have a picture of a signature. And you can see it has 8 stems: add, ask, assault, attack. And it has 4 suffixes. So null means nothing. So add plus null is add. Add plus ed is added. Add plus ing is adding, and add plus s is adds. So we've got 8 words and 4 suffixes. So we've got 32 words here if we expand it all. So what I'm going to do is, with whatever corpus I have, and again, I say I, but it's really the algorithm, we're going to find out all of the signatures that are there, and we're going to count up the information content of the signatures. And that will be much better, much smaller than the information content of the original word list. So a signature is at a higher level of abstraction than just words, but it hugs the empirical ground. It hugs the corpus, you might say. So with no knowledge of morphology, a list of words is just a list of words. And we know how to compute the number of bits in a list of words, but there's structure in a set of words. We know that as linguists. And structure for a linguist is the same thing as redundancy for an engineer. Boy, that took me so long to learn and to understand. But if, as a linguist, you want to talk to information theory, you have to accept it. It sounds almost like an insult that I spent my whole career discovering redundancy in languages. But that's what we do, and we call it structure. And the information theorist says, it's redundancy, let's get rid of it. And let's compress the data. They care about compressing, we care about structure, but we're actually doing the same thing. We're eliminating the redundancy, and we do that with morphology and syntax and so forth. Okay, so how do we do this? We do it with signatures. How do we decrease the description length? Well, we already know how to calculate the description length of a list of words. If we had 32 words, well, you know how to do the calculation. I showed you, you take the number of symbols, you multiply by 6, and that's what you'd get. But here with the signature, we have a lot fewer symbols. We've got 47 here on the left and 10 on the right, and that's 57. So we've really gotten a lot of compression, redundancy, structure by identifying these signatures, which is really at the heart of morphology. Let me just take a minute or less to tell you how you find signatures. You might say to yourself, well, so that's great, but how do you find signatures? And it turns out to be really easy for a computer to do it. Easier for a computer than for me or you, but all we have to do is alphabetize the words, and then we look at each adjacent pair of words on the list. So here's 3 words on the list: A, B, C, D, E, F, G, A, B, C, D, X, Y, and A, B, C, M, N, O. And so all you need to do is look at adjacent pairs of words to find out the stems. So A, B, C, D has these 2 continuations, E, F, G, and X, Y, just as A, B, C has these 3 continuations. So anytime you've got 2 or more of these proto-stems that have the same set of continuations, you put them into a signature. And that's really easy to do. So like jump and laugh might have, in a given corpus, have exactly the same set of continuations. So that gives us this signature. And on this slide, I have a few comments about problems that might arise, but let's not worry about problems. We can always come back to that. Yeah, this is also the problem. Okay, here is a screenshot. You might be able to blow it up with a finger if you've got an iPad. This is what the program, which is called Linguistic, it gives us as output. And I just want to say, I'm not expecting you to read this. Here we've got a list of signatures on the left, and it's sorted by the number of stems that it has. And the top one, which I've highlighted, says null S. And that is by far the most common signature in English. And of course, almost all of them are singular and plural nouns. And then the next one is null ly, which is like loud, loudly. They're adjective and adverb. Over on the right here is the same set of signatures, but it's sorted by how many suffixes there are in it. So the top one there, I don't know if you can read it. I'll just read it to you. Null, east, easterly, eastern, eastward, early, earn, earner. And if you think about it for a couple seconds, you'll realize that it's actually north and south are the stems that appear there. You've got north and northeast and southeast and northeasterly and so forth. So we can learn this structure automatically. It's more complicated than I told you, but you've certainly got the big ideas already. And I just want to show you a couple of diagrams that illustrate the output. So this first picture here, I hope you can read this. To me, it's actually fairly clear. This is I call it a lattice, and each rectangle is a signature, and they're in rows. And the signatures here on the bottom have 2 suffixes. And the next row, they have 3 suffixes. The next row, they have 4. Next row, they have 5. So they're organized by how many suffixes in them. And the ones at the bottom, the one on the left says nullness, so like loud, loudness. And the one on the right says null ly, so again, they're adjectives. So we have some adjectives that appear with and without ness, and some with and without li. And then we've got others that appear with both li and ness. And as we work our way up, we see other adjectival suffixes and the number of stems that they appear with. So at the top here, we've got null, est, li, and nest. So that's, it could be like, what's an adjective that it's not large because that ends in an E, and it's not, whoops. Screen sharing is paused. Do you still hear me? Do you still hear me? Okay.
Yes, completely. And moreover, we can see your screen.
Okay, good.
On the slide 53.
Right. Okay. So these are the sets of adjectival signatures that Linguistica finds. Here is something similar for verbs. The bottom, we've got two big families of verbs, as you might imagine in English, those that take null, ed, ing, and s, like jump or laugh. And over here, we've got suffixes, stems that take suffixes ed, es, and ing, be like love or move. And then each of them gets, can appear with a larger and larger set of affixes. Here's a lattice that shows you the finite verb in French and the first conjugation in French. The details don't really matter, but what you see is a common geometrical structure, this lattice that shows exactly what patterns of affixes appear together in a particular corpus. I have another set of slides. I'm not going to share them now. If you care, in a minute, I could go back to them. But I was recently looking at Swahili, which has a much more complicated set of prefixes, and you get an interesting result there. Okay, I feel like I only just started, but I suspect I've been going for close to an hour. So I'm going to draw to a close, really. And I hope I can say the following with a bit of humor, that it might sound like this if you had to summarize what I said. He talked about some mathy things that I didn't quite get. They involved probability, but not probability of the sort that I was taught in school. There was a lot of talk about logarithms and plogs. He tried to discover words from a long list of letters, and it worked well with some words and badly with other words. And how can you discover words if you don't know what they mean? Is this cryptography or is it linguistics? And he discovered a lot of morphology of English, but I don't know how he did it. Okay, that's fine. If that's what you come away with, that's fine. The way I would summarize it is this. I told you about MDL, and I gave you an idea about how it formalizes ideas that are important for linguists. And it does this in some very surprising ways. And they really do demand some thought and some justification and some reflection. And I illustrated MDL with word discovery, which was the context in which I first learned about it. And then I have used it also for morphology discovery, which is a much more difficult problem than I thought it would be. And so I will stop there, and I'm happy to engage in a discussion or answer any questions you might have.
So it's time for questions, discussion. As normal, we can ask questions by sending them to the chat or by raising our hands. So please come up with questions, remarks, and complaints. Yes, here is a question. Oleg Bilev. Oleg, are you here?
Yes, can you hear me? Hello?
Yes. Yes.
Yeah, thanks a lot for this very interesting talk. I have a very maybe naive question, I don't know. Just my first idea when I hear about minimal description length is, of course, about comparing analysis within frameworks and comparing frameworks among each other. And whereas I think we can figure out how to compare analysis within a framework because they at least have the same meta language, I wonder whether you can have a way of comparing different frameworks between each other or analysis within different frameworks, because how can we agree on the same description format for these frameworks?
Absolutely.
Do you have any ideas about how this can work?
Yeah, Marina asked me if I was going to talk about this, and I said, wow, that's really the next level, maybe a second talk. So absolutely, I do. And Marina and I are trying to develop a project right now where we can get different communities of or small groups of linguists who want to push their theory, and we're trying to develop a way so that we can literally all get together and count in bits what it takes. So I spent the year 2006 and 7 in Paris. I was on sabbatical, and it was a very fertile period of being away from my home department. And I actually thought about this problem a great deal, and I wrote a paper which I called Towards a New Empiricism for Linguistics, which was a little bit tongue-in-cheek. I mean, the title was a little bit tongue-in-cheek. But there certainly is a sense in which some aspects of what I'm saying here resonate with empiricist approaches to science. And so what I did mainly in this paper was ask, well, two things. First, I pointed out that after explaining a bit of what MDL was, I pointed out that MDL is a very natural connection to one idea in the original model of generative grammar, Chomsky's notion of generative grammar, where he tried to develop the notion of an evaluation metric, which he thought would be within a framework. You called it a framework. Today, he would probably call it a universal grammar. In any event, the length of a grammar naturally aligns with what he called an evaluation metric. But he had nothing comparable to the notion of how well a grammar fits the data, which here we've modeled with a inverse log probability of the data. And so in that paper, I first made the link to generative grammar, and then I suggested that in fact, you can raise this to a higher level in which people coming from different theories can come and expect to get a fair evaluation of their best result, so to speak. And the idea is this, that there has to be a fundamental or a ground level programming language, or another word that's used instead of programming language is a universal Turing machine. I'll say a programming language, but probably, in fact, what I write, I talk about universal Turing machines, but from a practical point of view, we might just as well say a programming language of a certain sort. So the project to bring together people coming from different linguistic theories, as you were asking, the project is going to bring together a group of people from these different fields, and they have to agree on a common programming language. And you might think that the game is over as soon as you say that, because you might think every programming language is going to give some preference or some head start to one group or another. But I think we can establish a fair way in which everybody can agree on a single programming language, which would ultimately be the universal Turing machine. And so, to make a long story short, the answer is you do it by negotiation. And in general, if everybody is doing this with goodwill, it should be possible to find a common UTM that everybody accepts. Once you do that, you then have to agree on a set of data that everybody's going to analyze. But once you've gotten agreement on those two, and those are two very different kinds of agreement, but they're both sort of scientifically reasonable, then you should be able to compare across different sets of assumptions. Yeah, so the bottom line is take a look at my paper. I'm sure I have it on my webpage. It's called Towards a New Empiricism for Linguistics, and it also appears in a book that came out around 2015 called something like Empiricism and Language Learning.
Yeah, thanks. I read this paper actually many years ago, and I was actually very inspired by it at that point. So thanks a lot for this. For me, it was a source of thinking about what to do with theory. I work in LFG actually myself, but it doesn't matter, I guess. I just, when I read this paper, I of course was inspired on the one hand, but on the other hand, as far as I understand computer science, you don't have an algorithmic way to come up with a Turing machine for an arbitrary program, right? You can't do it automatically. So I think whatever we do, at some point we will still disagree. People will say, okay, but you converted my theory in the wrong way. It's not, there could be a better, a more compact way of doing it, right? How can you prove that this is actually the most compact way of writing this program? That's, right, I guess, the main problem.
It seemed to me that that's not a problem for this approach, but it's not a problem if we don't think of it as, let me start that over again. We're not asking these questions of a mathematician, and we're not asking mathematical questions. We're really asking questions of scientists, and we want to get scientific answers. And for that reason, I believe it's perfectly reasonable to say that each team, call it a team, the LFG team and so forth, each team is responsible for coming up with the shortest program. And none of the competitors are going to say to you, oh, you know, you did a really bad job on LFG. I can't believe you're in charge of LFG and you came up with this. My first-year students could do a better job than you. Nobody's going to say that when you're present. You are responsible. And if you see somebody else doing a bad job, you're not going to tell them either. So I think it's possible to, you know, there is no guarantee that it's shortest, but that's true of everything. I mean, it's true in linguistics. You never know you've got, and you never do have the best analysis. You just do the best you can when you are. And so for me, the point is to go from what I was talking about in the slides, which is going from data to grammar, to raise it up a level to a social question. It becomes a matter of social epistemology or something. But I'm sorry I gave you such a long answer to when you knew the answer, but hopefully for other people it was helpful.
No, thanks a lot. That's very actually a reasonable, sounds a very reasonable way of doing it. Yeah, kind of sociologically taking it as in the same way we take theories and analysis. Yeah, thanks a lot. That's very a lot of things to think about. Thank you.
Yeah, right.
Other questions, comments, and remarks? John, would you mind if I ask you something too? Well, my question would be kind of obvious and very naive too, and I wouldn't be surprised if you have answered that question many times. So the question is, how minimal description length considerations connect to language acquisition? If language acquisition is inferring a grammar from the data, and I believe this is how many people are used to think about that. Well, then the question, then a reasonable question to ask would be to what extent this process is governed, or at least informed, by the minimal description length consideration.
Yeah.
Does that question make sense?
Yeah, absolutely. Absolutely, it does. And I don't have a simple and complete answer to it. The best answer I can give, though, is this, that when I look at psychologists who explore how language is acquired, frequently I find interesting and very clever experiments that give insight into what is going on inside the child's head. But for the most part, the experiments don't tell me anything that I want to know as a linguist. And so frequently psycholinguists have asked me the question that you did. And I say, well, the experiments that I hear about, don't really address what the grammatical knowledge is that the child has. They're generally just one bit of knowledge here, one bit of knowledge there. And so I'm doing this because there isn't any, I don't know of another way of gaining some idea about how a grammar could be inferred. And the psychologists are never satisfied with that for all sorts of good reasons. Some reasons good, some bad. But for example, the psychologist may say, you know, it's important that the child be engaged in the conversation. It's not just hearing a string of words. There's got to be some kind of conscious engagement here. And there's nothing like that in what you're talking about. Okay, well, that's true. There's a lot of stuff this model isn't saying anything about. And it's certainly possible that one could approach these exact kind of problems along with a semantic representation and see if it would help. But in my mind, the real answer that I probably wouldn't write it down, but I certainly would say it in public. And that is this. Once somebody comes up with an algorithm that does a good job of learning morphology or learning words or what have you, as soon as one person's done it well, then 5 other methods are independently discovered around the world. There's some kind of halo of knowledge. Once one person does it, then somehow the dam is broken and many other people come up with it. So that's really what I think is going on. That, you know, of course, there's a limitation to the way linguists think about the acquisition of language and think about the structure of language. And this approach that I'm looking at here is sort of at the extreme of the very austere side, the very much, there's no human beings involved here. So don't worry, there's just language, but no human beings and no brains. So it is an extreme like that. And it wouldn't surprise me at all if it were possible to pull together what I've done here, along with back 40 years ago, we would say a competence model. But if there were some way to bring this closer to the actual behavior of a child learning language. So that's how I look at it. It's the style of learning here is most consistent with this very austere, you might say, structuralist view of what language is. And yes, in a broader context, that's just really a small slice of reality. But I have not seen any effort made to solve the same problem, but using greater information that would be available. So I would be completely open to including more information about how the data is presented to the learner. So yeah, so that's sort of my answer, but there's one last point I'd like to add to that. And it's something that you've seen in the 2 examples I gave you. And that is that this style of modeling learning is not what's called batch learning. In batch learning, you sort of learn everything at the same time. And it may look like batch learning from the outside, but it isn't really. What the system is doing is learning the easiest things first. So like with learning the words, you know, I'd learned TH and then THE. That was so easy to learn. And with morphology, null S was so easy to learn. A lot of things are easy. Each language has the easy things to learn. And I think that's an important part of language acquisition. If we're going to model language acquisition, I think we need to respect the idea that each language has certain aspects. There would be phonology, morphology, syntax, semantics. Each language has certain aspects that are easier to learn than others. And this style of work, this MDL style, I think is a good way of acknowledging that. That's the best answer I can give you, though.
Thank you. The last point you made sounds very, very appealing, in fact, that a model of language acquisition should respect the intuition and the observations that easy things are required first. Thank you.
Yep.
Any other questions? Yes. Here is Stepan Kalinin.
Well, thanks a lot for your presentation, and that was very inspiring and very interesting. And I've got a number of questions. So you mentioned that you had started with dealing with information redundancy in languages, and I would kindly ask you some question. Is there some differences in value of redundancy or characteristics of redundancy in different languages? That's first, and second is there any correlations between typological parameters and information redundancy in languages? That's my second question.
Yeah, on the second, I don't know much about it. There are a number of people these days who are working on problems like, or asking questions about the amount of information flow per unit of time or per syllable or per word, something like that. And I haven't really followed that. And I want to say it doesn't interest me. And oftentimes that comes out as kind of smug. And I don't really mean it that way. But the fact is, I don't know much about how typological considerations bear on the amount of information. And I guess I would be interested to know more about it. The first question was about how, I'm trying to reconstruct the question. It was about the way information is encoded in different aspects. When you said the question, I was thinking about how there'd be different kinds of redundancy when you, for example, you've got the same grammatical features expressed on different adjectives inside a noun phrase and on the head of a noun phrase. I think the answer is I don't know. I don't have a good answer to your question. That may be in part because I have looked at a number of different languages with Linguistica here, but I haven't compared them quantitatively. And no doubt I should, but actually, so I'm going to answer a question that isn't quite the one you asked. What I find when I turn to a different language, one that's perhaps typologically different, is things that I expected to be really easy to do turn out to be quite difficult. So I'm constantly confronted by the fact that things that should be really easy, even a first-year student in linguistics can do it easily, turn out to be really hard for this kind of language acquisition algorithm. Could you rephrase or tell me again the first question, because I didn't do a good job of answering.
Mm-hmm. My first question. Okay, I can ask it another way. Is there more redundant languages and less redundant languages, or not, or I had a mistake?
Okay. Yeah, that's another really good question that I hadn't thought about, because the way I think about analyzing a language that I'm working on, whether it's English or Swahili, is I'm excited every time I can extract more information, because that means I'm doing a job as a linguist. But how much is there that I haven't gotten yet? Yeah, so if you look at a language, if we just focus on morphology for the moment, and we think about a language like German or Russian, I guess, where we've got case and number and gender marked on nouns and adjectives, and so it appears in a number of places, then that's a redundancy, or we can call it linguistic structure, and we can extract it. I suppose it's fair to say that I share the prejudice, perhaps, of many linguists, that all languages have the same amount of structure, but that's not really based on anything. And how are we going to ever figure out exactly how much information there is? Maybe before I die, we'll be able to have a first crack at that question. It's a good question. How much grammatical or linguistic information is there? Does that depend, for example, on size of the lexicon, the number of stems? You know, just something as simple as that. If you double the number of stems in your lexicon, then very roughly speaking, each stem, the information associated with each stem increases by 1, you know, as long as the frequencies are correctly adjusted. So, and 1 is a lot. 1 unit, 1 bit is a lot for every word. So clearly the size of the lexicon, the number of stems, and something similar will be true in the like inflectional morphology. So the person who can answer your question will have to, you know, go through the phonology, which wouldn't be too hard. The morphology, I suppose we know enough about morphology that we could probably give an approximation to how much structure there is, how much morphological information there is on average per word, or I guess per word or percent. No, not percent, per word. But then you get to syntax and it's harder, and you get to semantics, and I don't know how to go there. So that's an inspiring question that you asked, and I don't have an opinion.
Thanks a lot for your answer. That's great.
Okay. Other questions? Anything else to discuss? Marina?
All right. So in your slides and in your work in general, I think MDL is thought of as this pretty fundamental principle. So more than just a metric, something important that we should actually strive for, something almost like the do good science principle. And there's an alternative opinion that I have encountered, whereby MDL is simply a metric, which has its uses like all metrics do, but is just one way to evaluate the data quantitatively along others. So my question is, what do you think about it, and why exactly do we expect natural languages to be optimal in the MDL way? So why do we think that they will minimize this length of the corpus plus data, when in nature, not just in linguistics, but in nature in general, there are so many things that are just not optimal?
Yeah, Well, that's a great question, obviously. I think that my own orientation to that question is pragmatic in the following sense. It blew me away, so to speak, or how shall I put this? It astonished me when I first encountered DeMarkin's work on word discovery. And why did it blow me away so much? First of all, and this is irrelevant to your question, but first of all, because it raised a question that I had never thought of. I mean, I was a linguist, I was a grown-up, I had long been a professor, and I never thought about the problem of learning words from, a long unbroken corpus. How could I not? So I saw that this way of thinking about things led to a creative side that had escaped me. And then secondly, and this is totally relevant to your question, what I saw in DeMarkin's work, and this is clear as well in Rissanen, who developed this, is what they saw was that making no empirical assumptions still has worlds of consequences that seem empirical at first sight. So put this in a slightly different way. In computer science, people talk about supervised and unsupervised learning. And unsupervised learning is what we've been talking about here, where you're not given the answer. Supervised learning means you want to create an algorithm and you train it on certain problem sets, and then you let it out on the world. And unsupervised learning is very similar, except that you never give it the answer. You tell it a function of some sort, and you say, well, optimize it yourself in the way that that suits you the best. And an MDL-based work seems to do that with making almost no assumptions whatsoever. And when you go back and you see, oh, this is where the assumption is, that's where the assumption is, but they're really very, very minimal. And so the question can be asked, if we make no assumptions at all, what results come out of the work? And that's what DeMarkin was trying to do. And when I tried to replicate his work, that's what I was trying to do as well. And so this was in the late 90s, and it was about 10 years later, I guess, maybe less, I don't know. I don't really follow Chomsky's work that carefully anymore. But there was a certain point, I think in the early 2000s, when Chomsky said, oh, but we can even drop any substantive content to UG. And I thought to myself, oh yes, he's coming around essentially to the ideas of MDL. So I think a good answer to your question is whether MDL is the answer to the question, what is the mystery of the universe, so to speak, or the epistemological mystery of the universe. A more modest version of it is, given any set of data, let's take MDL to be the approach which makes the fewest assumptions, and let's see how well it will work. In the case of language, we don't seem to be able to, at this point, do an analysis that includes semantics, because we don't really know, or I don't know, how to quantify semantic information in a way that would be necessary. So it's always going to be it's going to be incomplete for a long time. And we're not really testing MDL as long as we can't include semantics in our model. And so when MDL-based models fail very badly, that'll teach us something. When they work well, it seems to support the idea that we don't, well, that we need less structure, less innate knowledge, less UG in Chomsky's sense. So sort of to get back to your question about the two views of the universe, or the scientific universe or the linguistic universe. So I'm more on the pragmatic side, which is to say, it makes a lot of sense for some people, including me and you, to explore how well MDL works. But clearly there are other people, and it seems to me deep learning is an example of the other people who are not really concerned with optimizing or minimizing use of resources, which in a way is what MDL is about. There's kind of mathematical resources that we're trying to minimize. And there are other people, as I say, people in deep learning who are not concerned with minimizing in that way. And they're doing really amazing work. But anybody who looks under the hood of a deep learning model knows that regularization is a really important part of getting a good model. And regularization is the sort of the technical term for cutting back, making the model, cutting 10% off the complexity of your model in order for it to work better on unseen data. So even in deep learning of any sort, there's a lot of thought that goes into, let's not fit the data too well, or we will be overtraining. Yeah, so that's my question, is I take it pragmatically.
Thank you.
Thank you, John. I believe we have no further questions and comments. So I would like to express my colleagues' deeply felt gratitude for you to be here, for your talk today. It was real pleasure and honor to have you at the colloquium of our department. Thank you so very much, and we would be pleased to re-invite you at the first possible occasion. Thank you.
That would be wonderful. That would be wonderful. I very much appreciate it. I don't speak Russian. I have 2 grandchildren now who speak Russian, and I am making an effort to be able to speak to them in their second language as well. And I hope that the opportunity for us to talk face-to-face will happen before too long. Thank you again for this invitation.